Okay, we're going to talk about black holes. I was sent an email by a student about a project where they needed to ask someone about black holes. And given how long the email reply was going to be if I typed it out, I thought I'd just make a quick video. Well, we'll see how quick it is, and post it to YouTube, and that can be my answer. So let's have a look at the questions. How do scientists know there is a supermassive black hole at the center of every galaxy? Well, let's start with our galaxy, because it's the one that we're in, the one we know best. If you look at sort of a random point on the sky, and you look at the stars, over time they will drift in a certain direction. The stars aren't exactly the same every night. Particularly closer ones will drift further. But on average, it'll be slow sort of drifting. They're all going around the center very slowly in a rotation, slowly on human timescales, of course. The sun is going around the center of the galaxy at about 220 kilometers per second. But there is a special point in the sky towards the center of the Milky Way, as we see it on the night sky, where something else is happening. There's a lot of high energy radiation coming out. There's a lot of radio waves coming out. There's a lot of X-rays coming out. Something is there. It's very compact. It's very small, but we can't precisely see what it is. And if we watch that for a long period of time and watch the stars going around that thing, we see something interesting happen. So this was work done by the Galactic Center group at UCLA, and they have watched these stars around the center of the galaxy since 1995. So that there, the star in the center there, is supposed to represent the whatever at the center of our galaxy, and all of the other points here are stars. They're not actually that big, that's just the telescope blurs them out a bit. So if you watch them, something interesting happens. Whenever they wander past this whatever it is, they take a very rapid U-turn. Up until the end of 2013. So what's happening here? What happens is this star takes a sudden U-turn in a couple of months. That's a billion tons of nuclear fusion reacting, burning star there, doing a complete U-turn in a couple of months. So there is something there in the middle there. It's not only producing copious, very high energy radiation, it's also very dense and very heavy. So what that's telling you is there must be within the curve there, within the U of the U-turn, there must be a lot of mass in a very small region for that to happen. And no known form of matter could stay that dense and still hold itself up at that size. It must have totally just collapsed into a black hole, into what Einstein's theory of gravity says is a complete collapse of matter and space-time. So that's why we think there's one at the center of our galaxy. There's a region where must be a lot of matter in a very small volume, and it's got to be a black hole, to be honest. So why then do we think there's one at the center of every galaxy? Well, at the center of most galaxies we see the same sort of pattern of very high energy radiation coming from a very small region. In particular, we see quasars, which are the ultimate in this. They produce amazing amounts of radiation. They can be much brighter than the entire rest of the galaxy that they are in, but we know from various reasons, from how their light flickers, for example, that they must be very small. They have sort of coherent changes of how bright they are over very short time periods, so they must be very small. And so we also see stars in those universes. While we can't see this sort of wonderful detail, we see them in very fast orbits, very close to the center. And so it's a reasonable conclusion that there is a very large, very dense thing, and no known at the center of those galaxies, and no known form of stuff could hold itself up. So there's supermassive black holes there as well. Question 2. Many sites say scientists don't know how supermassive black holes formed. Are there any theories? Well, we're not short on theories, that's for sure. So there's a famous diagram produced by Martin Rees in 1984. Rees is one of the sort of leaders of this field for the last couple of decades. So here's a diagram of some of the ways that we could end up down here with massive black holes. So we'll always start out with a gas cloud. The universe starts out as one great big gas cloud, which then collapses under its own gravity. Parts of this gas cloud will collapse under their own gravity. So there's a couple of options here. The usual way we think stars form is that as this gas cloud collapses, it will start to condense into stars as various parts become dense enough to fire up nuclear reactions. If that happens early in the universe, you may get a very dense cluster of stars. And then if those stars themselves combine, or if they, for whatever reason, make an awful lot of very big stars, once they go supernovae, going down this part of the diagram, we'll have a cluster of very dense things, either neutron stars or just smaller black holes. And then if that whole thing is still very tightly bound, very close, you could have one black hole that grows spectacularly, and then you've got yourself a supermassive black hole. Or perhaps they all sort of collapse together into a relativistic cluster of stars and neutron stars, smaller black holes moving at almost the speed of light, which will then further collapse. Another option is that either through this dense star cluster or via direct contraction of the gas cloud in the very early universe, when those clouds would be very dense, much denser than today, you get what's called a supermassive star. So the stars we see around us, I think the heaviest star known is about 300 times as heavy as the Sun. But in the very early universe, when things were much denser than today, you could have supermassive stars, and we're talking 100,000 to 1,000,000 times the mass of the Sun. Now these things burn out extraordinarily quickly. The Sun has about 10 billion years of fuel. These things, at most, we're looking about 1,000,000 years before they completely exhaust all the nuclear fuel that they have. And then you've got an awful lot of matter just sitting there without the sort of pressure it needs to hold itself up against its own gravity. So via various instabilities, I won't explain exactly what those are, we could have a small number of black holes form which then coalesce in sort of this sort of way as well, or you have a direct collapse into a black hole. The reason why we say that we don't know how supermassive black holes are formed, we have this set of ideas. It's plausible we know how to make them. The interesting thing about the universe is that they seem to be made very quickly after the beginning. So, for example, if we think that, as astrophysicists do, that quasars are powered by, what we're really seeing there is the matter becoming very bright as it has its last spiral into the supermassive black hole at their center. We see quasars from the very early universe. Now, you know that the universe started off very smooth, and so in a matter of less than 1 billion years, the universe has managed to create these supermassive black holes. Now, that seems pretty fast. And so the question is, which one of these processes is fast enough to do that? Now, one of the reasons why this is so difficult is that the physics is much more difficult. We're in much more extreme circumstances. An ordinary star, I can write down equations on a blackboard that give rough order of magnitude estimates about how big it's going to be, how long it's going to last, all of those sorts of things. But these supermassive stars, post-Newtonian there, means that we need Einstein's theory of gravity, which is much more difficult. We're talking about the very early universe, so much more extreme circumstances. We're not going to have, certainly with this generation of telescopes, the sort of observational clues we need to know which way we should go down this diagram. So we have theories, but we see quasars in the very early universe, and our best model of those says that only a very massive black hole could power that sort of thing. But exactly which way we go down this diagram to make something like what we see at the center of our galaxy, we're not totally sure yet. 3. Why does a star explode into a supernova when it runs out of energy? If it has run out of energy, where does the energy for the explosion come from? Okay, good question. Let's start with this diagram. This one's a bit busy, but I can take you through it. So what happens to a star over its lifetime depends on its size, depends on its mass in particular. So on the bottom here we have all the different sort of masses that you could have for a star. And then as you go up the diagram, these are the phases it will go through. So if you're too small, if you're down here, you don't really burn anything at all. These are the too small to burn things. They aren't really stars. They're planets or they're brown dwarfs. Then smaller things will be hot enough to burn helium, but they're not particularly hot enough to burn hydrogen. Sorry, wrong way around. Hot enough to burn hydrogen, not then hot enough to burn helium, and so they just kind of fizzle out at that stage. Our sun is here at about 1 solar mass, of course. There will be some burning of helium, and then it will enter what's called the asymptotic giant branch phase. What's happening there is that as stars run out of a particular fuel, they must stabilize themselves somehow. That burning of the fuel is what's holding back gravity. It's what gives the pressure, the thermal pressure, to hold gravity away. So gravity's pushing in, pressure's pushing out, and the whole thing is stable. As a certain fuel supply runs out, it must switch fuel supplies, and stars tend to sort of splutter as they do that. So the giant branch is a phase where the star's undergoing a lot of changes to try and get back to an equilibrium. These are the interesting bits where you make planetary nebula. So parts of the outer part of the star will be blown off in very interesting patterns that look like these. So some of the most beautiful things we see in the sky are stars that are trying to get used to this new fuel supply that they've had to be put on. Why do stars explode? Well, at the very high end here, very massive stars will be very hot. So once they run out of hydrogen, they can fire up helium. When they run out of helium, they can fire up carbon. When they run out of carbon, they can fire up neon. All of this is happening at the center. And so what you get is actually an onion layer to the star. So the center is the hottest, it's where it's burning fastest. So when it's burning neon, there's an outer bit that's still at its carbon burning stage, surrounded by a bit that's still at its helium, still at hydrogen on the outside. The problem with this is that once you get to iron, there's no more nuclear energy to be gained from fusing iron nuclei together. That is not a process that makes energy, it's a process that costs energy. So that's no good, right? The gravity's pushing in, and now the reactions would actually drain the pressure, the thermal energy, so they just continue collapsing. So what happens is that the core will totally collapse into a supernova when you're at this stage of the star. What happens is, and the details aren't totally clear, but we know that there is a catastrophic failure of pressure support. That suddenly there's just no nuclear fuel left, and so the outer layers collapse into the center. Now it's in those outer layers collapsing that there's a few ways that this could then cause an explosion, right? Where everything's falling in, we need it to go back out again. There's probably things like magnetic fields and turbulence involved, but one of the sort of main theories about how this works is that the very center of the star releases, as all these layers collapse in, they sort of bounce off that iron core and release a whole heap of neutrinos, very light, usually totally imperceptible particles. But they, as the inner core collapses, it releases these neutrinos from those last processes as it's collapsing onto the iron core. Those blow off the outer layers. So that's where the energy comes from. It comes in that collapse, that the inner layers, their last little bit of energy is used to blow off the outer layers. So that's what we see when we see a core collapse supernova. If the star is initially bigger than 25 times the mass of the Sun, that collapse to a supernova, what remains after that carnage is a black hole. Why do extremely dense objects have so much gravity? Depends what you mean by how much gravity. Let's think about it this way. Here's what's called the escape velocity. So one way to say, how strong is the gravitational field that I am in is to say, how fast would I have to go to escape this gravitational field? So ignoring the air around the Earth, how fast would I have to shoot a cannonball upwards for it to go up and never come down? So it's not true that whatever goes up must come down. If you go faster than the escape velocity, ignoring things like wind resistance, you go up and you never come back. Gravity will not, you're going too fast for gravity to be able to draw you back. So you can see what this depends on. G is the gravitational constant, so it's the same for everything everywhere, but then it increases with mass. So the more massive a thing is, the harder it is to get off its surface. And also the radius where you start your journey. So if you take the Earth as it is, and you try and get off the surface of the Earth, then that is r is the radius of the Earth, 6 and a bit thousand kilometers. If you took the Earth and squished it down further, the mass would be the same, but the radius would be smaller, and so the escape velocity would be higher. You would be sort of deeper inside the gravitational well. You'd have to go faster to get out. If you take that formula and you set the velocity equal to the speed of light, then you've got something pretty interesting, right? You would have to be going at the speed of light to escape that thing from that radius. And so if you're inside that radius, or if the thing's slightly heavier, then you'd have to be going faster than the speed of light to escape, so you don't escape. You can't go faster than the speed of light. That's what a black hole is, and that radius is called the Schwarzschild radius. So that's the sort of the size of the black hole. So extremely dense objects put a lot of mass inside a very small radius, and so if you want to escape from them, from close to them, you need a very large escape velocity. And if they put enough mass within a small enough radius, then you've got yourself a black hole. Does a black hole really blow out matter sometimes, and why? The answer is not really. It's not the black hole itself that blows out matter. If we're talking about black holes in an astrophysical context, things like quasars, things like the thing at the center of our galaxy, we do see lots of radiation coming out. We also occasionally see matter being shot out very quickly. Now the poster boy for this is called Cygnus A. So this is a picture in the radio of the radio waves emitted. So that at the center there's a galaxy there, and shooting out either side of this galaxy in a very thin and narrow stream is very fast jets of matter. And the collimation, the straightness, the thinness of that beam is just amazing, because it goes over a very large area, and you can see here as it starts to plow into the stuff around it, it's lighting up that as well as the jet, as this is called, sort of grinds to a halt. So this is called a jet. We see these around various quasar-like things, active galactic nuclei they are called. We think that for the same reason we need something pretty extreme to make all the radiation in quasar, we need something pretty extreme to make this sort of jet. The best models we have are that as matter has its final plunge into the black hole, it's sort of swirling around in a disk. Some of that matter, due to magnetic fields being spun up there as well, instead of spiraling in, will spiral up along the axis and be shot out instead of going into the black hole. So we can see other examples of this. This is called Cygnus A. It's a galaxy, and we see these plumes of matter being shot out from the very center. So this is in contrast to other galaxies we see where we think it's supernovae, which is sort of blasting things off. So you see a sort of wide wind of matter being blown off. This is obviously a very narrow shaft. And if you zoom in, that's what this bit is, you still see a very narrow shaft of things pointing away from a very small object. So when a black hole consumes more matter, does its gravity increase? Yes, because its matter increases. As it eats matter, as the matter goes past the point of no return, past that Schwarzschild radius, it adds to the mass of the black hole, and so the black hole gets bigger. It's important not to think of a black hole as sort of a cosmic vacuum. If the sun became a black hole right now, first of all, we wouldn't know about it for 8 minutes, because that's how long it takes light to get here. But in terms of the orbit of the Earth around the sun, we'd still be fine. We wouldn't be getting sunlight, which is probably a bad thing. But we're not. We can still orbit around it fine, because the gravitational attraction we feel only depends on the mass and the distance. And so from the Earth to the sun, they stay the same, and so we'd continue our orbit around this thing that wasn't giving us any sunlight, but in terms of the orbit, it's just fine. We would not be instantly sucked in. So it's not that black holes suck in stuff any more than, planets suck in stuff because of their gravity. What's different about a black hole is that it's a prison, not a vacuum. Once you're in, you can't get out. So 7, can black holes die? So for that reason, the answer is probably no. It's certainly astrophysical black holes are a one-way street. Stuff goes in, stuff doesn't come out. There's 2 caveats to that, though. Within the Einstein's theory of gravity, which describes black holes, there is a solution which is the reverse, the time reverse of a black hole. It's called a white hole, for obvious reasons. What that would describe something which was like hitting reverse on a black hole. What you would see is something just continually spewing out matter at almost the speed of light and continually getting smaller with time. Now, we've never seen one of those in the universe. It doesn't seem like the sort of thing that would be in our universe, but that's at least allowed by the theory. That would be, I suppose, a white hole is kind of a dying black hole instead of a growing black hole. But there's another possibility. Even within black holes in our universe, there's something called Hawking radiation. So this is one of the reasons Stephen Hawking is famous. Hawking radiation says that near the event horizon of a black hole, near that point of no return, there's the Wikipedia article if you want to read more, quantum mechanical processes will actually lead to the radiation being emitted by the black hole. It will be extraordinarily weak radiation for any sort of reasonable-sized astrophysical black hole, but it will be there. So in the very distant future of our universe, when black holes have sort of sufficiently cleared the region around them, they will start losing radiation, and because matter and energy equals mc squared, the same thing really, it will slowly leak away its mass. And so over an extraordinarily long time period, if this idea is correct, black holes, even black holes in our universe, will die. Where you once had a black hole, if you wait long enough, you will eventually just have no black hole and some very low energy radiation. Is it possible for a black hole to have another side? And if so, what could it be? So this sounds a bit like science fiction, but there is something interesting going on here. This is called a Penrose Diagram. So if we're trying to think about a universe with a black hole in it, so that's obviously something that's infinitely big, and we're thinking about that through time. So what Penrose did was, find a way of representing that in a finite area, so in a finite diagram basically, so we can see what's going on. So if you take an ordinary black hole, a Schwarzschild black hole it's called after its discoverer, here's our region outside the black hole, and here's the region inside the black hole. And when you describe this using coordinates that can handle all of this, you find that there's a natural way of extending those coordinates, extending the universe that it describes mathematically into a parallel universe and a white hole, as I mentioned before. Now, in this particular case, as you follow a particular thing, as it falls into a black hole, it crosses that point of no return, the horizon. There's only one way for it to go. It's hitting this, the singularity, that is supposed to represent the point at the center of a black hole at which everything just gets shredded, where all the matter has ended up, where really general relativity, Einstein's ideas about gravity, it's where they go to die as well. We don't really know what's going on there. The interesting thing happens if you make the black hole rotate. The way to do this, so Schwarzschild had made this discovery in about 1915, the way to describe a black hole using Einstein's theory. 1915, 1916 maybe, in the very early years of general relativity. Einstein presented his theory in about 1915. But it wasn't until 1963 that Roy Kerr, a New Zealander, worked out how to describe a rotating black hole, what's called the Kerr Metric, or Kerr spacetime. Now the interesting thing about this is that the singularity at the center of a Kerr black hole is not a point, it's a ring. So if you hit the ring, you're in trouble, but you can actually go through the center of the ring. So if we start in our universe here, and we go into the black hole, and there's actually two horizons in a rotating black hole. There's a region from which you can escape, but you can't stay still in a rotational sense. So I can get out, but I can't stop myself going around. That's the outer horizon. And then there's an inner horizon which acts like the Schwarzschild one, where you're going towards the center no matter what. Well, I was going to say it's game over, but it's not, because if we do what we did with that other spacetime and extend it in that natural way, this is the sort of diagram that results. And we could end up in an anti-gravity universe. That would be the sort of white hole case where we go through the singularity. Or we could end up in these other universes. So in the Schwarzschild case, from here, I can't get there. I can't get to the parallel universe, because once I'm inside the black hole, I can't. I'm going towards the singularity no matter what. But in the rotating black hole, I can get to these other places. And in fact, if I stay inside the black hole, what happens is that there are paths which are called closed time-like curves. What that means in layman's language is time travel. If you plan the right trip through a rotating black hole, you meet yourself going in the first place. You could arrange to play a game of poker with yourself. Or you could be spat out in one of these other universes. Now, here's the thing. This is just theory, right? We have a theory of gravity given to us by Einstein, which is the most successful, handles all the data as we have given it so far, and we say, all right, what does this tell us about what would happen inside a rotating black hole? And this is what it tells us. Now, the problem is, if you say what happens outside a rotating black hole, we can test that. We can see, we can point our telescopes. What happens inside, we have no idea. If you sent someone in to find out, they could not come back with the results of their experiment. So that's the status of this diagram. It is what our best theory tells us, but is not the kind of thing that we can actually test, short of actually going and jumping in. be quite a dangerous mission. But if you ended up in one of these other universes, you would be there thinking, hey, you know, this idea was right after all. This idea that actually the Kerr, the rotating black hole, is a portal to other universes is right. You can't send that information back where you started. But if the satisfaction of knowing that is enough, then maybe it's worth jumping in. So that's black holes. There's plenty we don't know. But there's also a lot that black holes explain about the universe, which nothing else that we know of can explain. So if you have any more questions, just why not ask me in the comments. Thanks.